With the procedures, this is a Masterthesis defense for Rafael Petersen, who comes from the Karlsruhe Institute of Technology, KIT for short, but he did his work at MIT. So we decided that we follow MIT structures for the Masterthesis, and he gets 45 minutes presentation time and then questions. Questions should be hard and fair, because it's a thesis defense after all. But in the 45 minutes, Rafael can present, and you can ask questions only if there are clarifications, no big discussions. Right? So that gives him time to unfold the story and everything. After the presentation and after the questions, I think Uli Lemmer, who is Rafael's professor at KIT, and I will discuss a little bit about it, and then Rafael has to also submit an excellent thesis, and then he gets his grade on that. I think that's the framework. Now, with that out of the way, you know what's going to come in the next 45 minutes. Rafael is presenting, but before that, I get a chance to introduce him. So Rafael Petersen, as I said, comes from Karlsruhe Institute of Technology. He has a bachelor's from there in electrical engineering, and he did his master's thesis now with us at MIT for 6 months. He started in January. And that was a lot of really good research that he will present to you. 6 months passed very fast, and it's a bit of a pain to see Rafael leave, because in the 6 months he managed to leave a big impression. He will talk about his research by himself more and show you exactly why I think it's great. So I'll talk a bit about Rafael and his context in our group. Rafael is certainly unique in many aspects, partly because he has an interesting filter. Some of that is probably Germanness. The other thing is purely Raphaelian, but he certainly didn't always sort of align with the Anglo-Saxon or American way of saying things. And that created a lot of laughter and fun moments for us in the group. He is very giving and sharing about his experiences, and always ready to help. So when you see him down in the lab and there is a problem that somebody has, he would jump onto this. He would connect people with friends and family to help with the research at a sort of moment's notice. And that was also apparent in his engagement in the broader MIT community. He was the communications officer for VISTA, which is the MIT Student Association for Visiting Students. And he has helped revive this association after the pandemic. And I've seen a very flamboyant and very grateful letter from the MIT officer for that VISTA program, thanking Rafael profusely. So you can see that his engagement didn't only sort of end in our group, he was also contributing to MIT on a larger scale. So I think both KIT and MIT can be proud of Rafael. And now not only has to defend his beautiful work in a stellar thesis defense, and then a written work. So Rafael, the floor is all yours.
Thanks a lot. If it would just be an only. I'm going to switch the microphone for that. I hope that you still can hear me. If that's the case. All right. Then I see if I'm on the slides here. Okay. All right. Then let me start. First of all, welcome to my presentation about deformation sensing and object identification with Elastochromic Photonic materials. I'm really glad that you all joined, whether it's live or I've seen over 30 people already online. So I'm feeling really honored that you joined my presentation. And before starting with the presentation, I should probably shortly mention why I'm currently talking in English. And the reason for that is, I mean, you have heard the introduction. I'm currently not at KIT in Germany, but therefore at MIT in the United States, where I've had the chance to write my master thesis over the past 6 months. And once MIT and Matthias accepted me to come over to MIT, Matthias suggested to me all the beautiful topics that his research group is currently working on. And as you can see, it's a broad variety of cool topics in the field of optics and photonics. For example, a miniature dark field microscope, the growing process of nanostructures on butterfly wings, droplet conformations to sharp different lenses, or the encroach of algae inside of water once increasing the light amount coupled in the water. Then there's also been work on fibers that change their color when being stretched, and finally also the topic I ended up, the Elastochromic Photonic materials, which I choose to work on, and I'm extremely glad that I had the chance to work on that, because the past students also wanted to work on that. So there needs to be something special about that material, but I think once you see it in real life and you can touch it and play around with it, you also have a lot of ideas popping up in your mind what you could do with that material. And once I knew that I wanted to work on that material, and by some hints from Ben, I got pushed a little bit into the direction of soft materials and also into soft robotics, and I found a beautiful TED talk from Giada Giabboni about soft robotics and the progress of soft robots in the past years, and that they might be the future for robots itself. So she mentioned that the interaction between soft robots and humans is the best that can happen, because there's no damage that can be created since such soft robots are softer than human beings. And one of the most difficult things in the field of soft robotics is to create soft actuators and soft sensors as well, because otherwise those robots will not be soft anymore. And so the idea is, why don't we just use this color-changing elastochromatic material to apply it to such soft robots as a sensor, and therefore still gain the ability of having a soft system. And before we now dive into the topics of that, let's maybe take a step back and have a look on the physics behind that material. And to understand how that material works, we need to understand how color works. And there are basically two ways of creating color. The first one is presented on its slide right now, and it's, I would say, the more boring way, so just having some pigments that can be added to for example, paintings, and then we create these colors by absorbing a specific amount of light and reflecting the other amount of light, and maybe all the colors that you see currently in this room, but also in all the paintings, are created by that amount of creating color. The more, I would say, cooler way of creating color can be found mostly in nature, because nature is one of the best designers of that, and that is structural color. So for example, butterflies, or what we can see over here, a peacock wing, consist of such structural color, which is nothing else than structures in the order of the wavelengths that then interfere or interact with the electromagnetic waves, and act kind of like a filter, so let a specific amount of light going through that object, being transmitted, or like reflected, and therefore creating those colors. And to understand those structural colors is also one thing that we need to do, because the material itself is also nothing else than a kind of structural color. So we can easily look on one object in nature, like this Japanese jewel beetle that has a beautiful green color, by a transmission electron microscope. And once we do that, we see that it consists of nothing else than alternating layers with different refractive indexes. And if we plot that in a more easier way, what we can see on the bottom left side, this is nothing else than a Bragg mirror, which is also the easiest example of a structural color. And we can see that those structural colors consist of alternating layers which are in the order of the wavelengths. So here, for example, a quarter of the wavelengths. And once we create this alternating layer of a quarter of the wavelengths, what the Bragg mirror does, we will reflect only the wavelengths which is 4 times bigger than the quarter of the wavelengths layers. And thereby we can create a filter that, for example, just sends back red light and lets blue and green light through. Or if we decrease the thickness of the layers, just send blue light back to the observer. And this is the same principle that was used for this color-changing elastochromic material, because there's just a photoelastomer which is applied to a reflector, and then once we irradiate this photoelastomer with a light source which has a coherence length that is bigger than the photoelastomer itself, we can build up a standing wave inside of the photoelastomer. And then where the maximums are in this photoelastomer, or from the standing wave, there will of course be a developing process occurring, and therefore the refractive index will be changed, and at the layers where the minimum is, there will no change in the refractive index taking place. And so we basically build up another Bragg mirror, but with the ability that it is still an elastomer, so it has a Poisson's ratio of around 0.5, and once we stretch that material, it will of course also decrease in thickness, and therefore also the layer thickness will decrease. And as we imagined from the slide before, once we have a thinner layer thickness, there will be in other wavelengths that will be reflected as a peak wavelength, and therefore we can create different colors, as we can see it here on the right slide. Like when we have the Bragg mirror created with the red wavelength being at the peak wavelength that is reflected, then once we increase it, we shift through the whole spectrum, so green and blue once we increase the stretching. And now that we know the physics and the principles behind that material, let's have a look on the work that I've done when I've been around here. And that was basically, first of all, to verify whether I could use this material as a sensor in the field of soft robotics. Then I also wanted to implement it into use cases. So first of all, a soft robotic bottle gripper, and then also a multi-bistable metamaterial. We will come to that later in the slides. And then, of course, we will also have a close look on the conclusion and outlook, what can also be done. But let's maybe first start with the sensor verification. And to verify whether I could use this material in the field of soft robotics, of course, I needed to first learn how to build up such soft robots. And during my time over here, especially in the first weeks, I got to know that for soft robots, one usually just creates a mold, which is the negative of the soft robot, fills that up with the material out of which the soft robot should consist, so a soft rubber, which is in the first state usually liquid, and the two components that we can then mix and then cure inside of the mold, and then in the mold it will cure, and we can remove the ready soft robot out of the mold afterwards. For example, with this mold, we just create a skin of a soft robot. And then with some adhesive and the color-changing material, I was able to fastly and easily apply the color-changing material to such a soft robotic system. and we can see the sheet that I produced ended up as being what we can see here on the right side. So 3 layers, and it worked quite good only for playing around for 1 or 2 weeks with that. There was a good result, but I can still say there's one problem that occurred, and this was once I looked on those samples after a few days, I saw that it didn't look like this beautiful red sheet that we see on top anymore, but therefore there was some inhomogeneously aging taking place, and a shift to green took place. And we knew that this shift to green did not occur when the color changing material itself was freestanding, so not in contact with the ecoflex layer, and therefore we assumed that there might be a diffusion process either of the polymers from the ecoflex into the soft robotic, into the color changing material, or the other way around, which then leads probably to a deswelling and therefore a color change or a change in refractive index. So I don't want to go too deep into the detail, but in the first weeks I just developed a system or a 4-layer approach that then was able to withstand those agings. So I just encapsulated the color changing material between a black backing layer to saturate the colors, and then a Solaris layer, which is a diffusion blocking layer, to stop the diffusion between the assumed diffusion between the particles inside of the ecoflex and the color changing material. And we can see that with this approach here on the right side, I was able to realize such a soft robotic system, which at least for the human eye did not age anymore that fastly. And we can look through the whole system on top of the color changing material and still see the sensor being in there. And once that was done, of course, I wanted to verify if this approach with the 4 layers could now be used as a soft robotic sensor. And for that, I looked up a paper and luckily found towards Perceptive Soft Robots, which is a progress report from 2018 mentioning the probabilities that need to be fulfilled, or the properties that need to be fulfilled to have a good sensor in the field of soft robotics. The first one is that the soft robot sensor needs to have a low Young's modulus, so to not inhibit the movement of the soft robot, of course, the sensor also needs to have the same Young's modulus or around the same Young's modulus. Then the sensor needs a small footprint to not affect the soft robot's behavior. As we can see over here, for example, for a multi-gate robot, there was a research group inventing this actuation system, and we can already see how it overgrows the whole soft robot and therefore inhibits the movement a little bit. And if this would occur for the whole sensor system as well, we had a huge problem. And then as for every sensor, I also needed to verify that it is resilient and show that the resilience and durability are fulfilled so that I can stretch it often enough without tearing, that I don't have a color change over time and all that stuff. And the last thing is just the robustness. Such soft robots have a huge benefit because they are extreme robust, like here a car, for example, drives over it and it still works afterwards. But if there is a color changing material being applied as a sensor and that would not withstand that, then of course the soft robot could not be used anymore. And so for the first point, I also don't want to dive too deep into that, but I just calculated or compared all the Young's modulus of the 4 layers that I had in the system, and we can see with 500 kilopascal, 90, 923, and 564 kilopascals, this is all around the same order. So we can say it's not exact the same Young's modulus, but it is at least close enough to each other. And since the layers are really thin, the interaction between those layers hadn't been a problem for stretching that at least I have used in my work. Then, as the next point, I wanted to show the spatial distribution, so whether I have a good spatial distribution and whether the sensor is limited in dimension. And luckily, this is just a 2-dimensional sheet, right? The third dimension is only a few micrometers in height, so we can neglect that. And by means of net shaping, we can basically arrange this layer around every 3-dimensional object by just cutting out the surface of that device. And then, for example, I implemented this hollow-shaped or hollow donut-shaped ring gripper, where I could, for example, grip a syringe with that and could apply the color changing material, and as we see, it didn't change anything of the properties of that material, except that we then see how much volume is inside of that soft robot. So from the top to the bottom in those 3 cases over here, it's the same volume in the hollow-shaped donut, but there's no change in the properties of that soft robot that we can detect. Then for verifying that the material doesn't age and that I could stretch it often enough without getting into a mechanical problem, I set up the system that we can see over here, where I had the light source feeding in light into an optical system that then collimated the light on a sample of the soft robotic material with the color changing material. And then of course, almost all the light is going to be absorbed by the black backing layer, but the peak wavelength is going to be sent back into the optical system and then sent into a spectrometer where I could just analyze the spectrum of the sample. And then the sample was saved on a computer, while this computer also actuated a motor and transferred the rotational movement of the motor via a Slater crank mechanism in a linear movement to stretch the sample. And then with the sensor being applied, I could see whether I'm currently in a stretched or in an unstretched state. And then every 10 times I drove through the stretched state, I said to the computer that there should be a spectrum taken in a stretched and unstretched state. And to prove that I did not lie, this is the real setup that I just set up in our optical room. So once again, nothing else than the light source being here, that fed into the optical system, the motor that drives the stretching of the sample, the motor controller for controlling the driving speed of the motor, and the spectrometer at the top right over here. And we see that the results with the 4-layer approach have been way better. So over a course of 10,000 cycles of stretching, there's almost no aging taking place. So we can say that in the stretched and unstretched state, so unstretched state at the top and stretched state at the bottom, yeah, it's kind of a straight slope, so nothing, no aging taking place. For the robustness, I wanted to do or to test the materials and the 4-layer approach in a more harsh environment, where I just set this color changing material with the soft robotic system once in water and floating water over a course of 8 days, once in an oven at 70 Celsius degrees, and once just in the lab, so a reference sample without another temperature and another humidity, and then observe how the spectrum changes over a course of 8 days. And I also wanted to do a maximum stretchability test, as we can see with the device here on the bottom left side. And the results of that have been that for the reference sample, of course, there should not have been happening anything after the first measurement that I've also done, and this is also what came out here. So over a course of 8 days, the peak wavelengths in the unstretched and stretched state stayed quite constant. There's some varieties that come from setup inaccuracies, because I needed to get the sample out of the measurement system and back in that after each day. But that is a quite good result over here. Then the same for the water sample, so being in floating water. Also here is no aging taking place that can be observed, also just some setup inaccuracies. The only thing that I mentioned is that after 8 days, and this is also why I stopped the measurement after 8 days, that the peak wavelengths in the stretched and unstretched state have been the same, and the reason for that is that the sample tore when being stretched after the 8th day, and so one can say that the mechanical stability of the sample had problems, but with being in water, but the peak wavelengths was not a problem, so aging of the photopolymer was not a problem. And then for the last sample, we can see a significant aging in the first 3 days, which might underline that there is a diffusion process taking place, because diffusion is usually proportional to temperature, and so the diffusion coefficient as well as the diffusion length increases in the when increasing the heat. However, we can see that after 3 days, there's no aging taking place anymore, so it might be possible to just produce the color changing material in the infrared state and then pre-age it in the oven over a course of 3 days to let it shift into the red peak wavelengths, and then it should also be stable in this surrounding. And then for the maximum stretchability, we see a reference sample over here on the top right with 0% strain, so still being in a red color with the peak wavelengths. And then I just wanted to see how far I could stretch it without being destroyed. So we see for 30, 56, or 95% of stretching, we shift through the whole spectrum, but there's no destroying, which we can see. However, we should not stretch it more than 100%, because after that we shift into UV, so we cannot use the sensor anymore, especially not when we want to use a camera system for analyzing that. But if we do so, we see at 140% there was the first tear occurring, and then of course if I stretch it more and more, there are more tears occurring. So we should definitely not use it over 140%, but it is also not recommended to use it for more than 100%, because then we cannot sense anything with the system anymore. And now that I know the conditions under which I could use this material, and that it at least fulfills the points that have been mentioned in this progress report from 2018, I also wanted to realize 2 systems or 2 use cases where this material could give us an improve. First is a soft multi-bistable metamaterial where I spent some time on, and the other thing is bottle recognition and sorting system, which we can see here on the right side. And since I'm getting, hopefully after this, a degree in electrical engineering, I'll just start with the engineering task, so the soft robotic bottle gripper system. And to understand why I wanted to work on that, we need to see the point on how I get to this point. And for doing that, I just looked around through the internet and found a nice video from Galileo, a German television series, mentioning a huge problem currently occurring in the German beverage and bottle recycling system. And to understand this problem and how I could find a solution to not have this problem in the future anymore, we first have to have a look on the system itself. And in the past, there have been several companies, for example, several beer companies, producing their beer, filling it up in bottles, and then customers just bought that beer, drank it, brought it back, and got a little bit of money back, and then the bottles could be washed out and shipped back to any of those companies. And this cycle could be run through up to 50 times, so really good for environment, good for reducing plastic, basically something we should not or don't want to change. However, in the past years, there was the evolution of the bottle shape diversity, so we see that especially in Germany there has been beforehand, so in the past, normalized bottles like the NRW bottle or the Euro bottle, which have been used by all the beer company providers, and so no huge variety, so every company could basically get back the bottles of every other company. However, the companies figured out that customers tend to buy more beer if the beer bottles are having a signature on top there, so kind of a texture with their own logo. And so it happened that all of the bottles that currently are on the market, or most of the bottles, are now having such a texture because it seems to be more premium and more people tend to buy it. And the problem of that now is, I guess most of us will already know, is that Golsch, for example, don't want to have a bottle from Krombacher because they don't want to fill up their beer in there. So the current system is that we have several companies producing those bottles, so 1 to 3 different bottles. Still people buying that, drinking that, bringing it back for getting a little bit of money, and then there needs to be something new. The human who's just sitting there for 8 hours a day and sorting those bottles into containers to ship it back to the right company. And this is a horrible job, I guess, that nobody of us wants to do, and also yeah, the person needs to be paid, so that means also the prices of the bottles will be increased, so all in all, kind of a lose-lose situation. And I asked myself, why is there not already a robot doing this stuff? Because it's simply just a work where bottles need to be sorted, right? That should probably be done easily. And especially if we have a look on the photos of those bottles, I mean, we can detect those textures on there just by looking on them. However, there was also a news article mentioning why there is no solution for that so far. And the reason is that the photos over here are taken from a professional photographer for advertisement. And if I just take the same bottles that luckily my brother brought to me when he visited me, we can see that the texture over here cannot be detected anymore. And the reason for that is that once I take the photos, even under good light conditions in the lab, it still is not able, or I'm still not able to make that beautiful photos where the texture pops out, especially if it's on the same background, like brown on brown or green on green. And so this is not what we get in a usual industry case, but more what we see on the right side, and so imaging system is not able to just sort that back. And that was the point where I thought, okay, we have some texture and we have a color changing material that once we apply it against the texture, lets the texture pop out, so why don't we just use this as a soft robotic bottle gripper? And then I thought about how should that look like, and of course it needs to be cylindrical to, besides detecting the texture, also be able to grab the bottle. Then we need the color changing material in contact with the bottle to have the texture being pressed against this color changing material. And then we need a transparent soft robot body, so basically the same layer that I just developed to see through the whole system on top of the color changing material. And so I ended up with the black backing layer and the color changing material in the inner side, and the diffusion blocking layer, and then the soft robotic material with the chamber here to just be inflatable and press against the bottle, and then outer system is just a rigid tube, which is also transparent, so polycarbonate or acrylic, for example. And for realizing that, the biggest task was just to upscale this layer that I just showed to you in the previous slides, so to make it possible to create a huge layer out of that, and then attach the ends of those layers to form a tube, and then wrap it around another acrylic tube to have that whole system. And the biggest challenge in doing that is just to realize that the layer is still homogeneously enough, because otherwise we have different thicknesses and therefore different pressure when inflating it on top of the surface. And the other thing is just to reduce the defect density so that we don't have too many dust particles in there, which reduce the quality of the color that we see. And I ended up with the system that we can see here on the right side, so basically just this layer that I introduced to you, attached the ends to each other, and then wrapped it around the acrylic tube. And then I used some affixers to enclose the chamber in the middle side, and with a syringe I could just inflate the system to grip the bottle. And we can see that on the left side, this is the overall design that I ended up with for the system. And to not only verify that I was able to lift up a bottle, but also that I could detect those textures, and since I wanted to make my life a little bit easier, I reproduced the system in a flat-shaped form, so just used the layer without being attached at the ends and pressed it between two acrylic tubes, and placed over one side in a hollow die that I could also inflate to have a system where I could just press out this color-changing material with the soft robotic material against anything like the bottle in the setup that we can see here in the middle part. And we see once I press that against the texture, I see on the right side the Golsch logo. This Golsch logo pops up quite clearly out of that structure, so we have a higher contrast between the background And I once again have to mention that the logo that has been taken with the photo over here was taken by a professional photographer, so it would not look like this if I would have just taken it inside of our lab. And then I wanted to show that we are even able to detect those with a computer, so I made my life one more time easier. We will come back to the bottles in the next slide. But since I had a flat-shaped system now, I wanted to detect flat structures at first, so I printed out some textures at first with our 3D printer, like the LBPE logo from our lab over here, and pressed it against the color-changing material, took some photos out of that, developed the software which could basically binarize those images, so from RGB transferred it to HSV room, use the U channel, and then just the threshold method to binarize that object. And then with the cleanup process, which based on morphological operations, I just cleaned out this image a little bit to get the shape back. Then I did a binary comparison, so between the cleaned up mask that I detected and the logos, for example, LTI from the institute I'm working in Germany, LBP or MIT logo, and did a binary overlap, and we can see that with the binary overlap, so the simple approach, we can even now see that there is a detection possible because the highest overlap happens for the real texture that should be detected. So the computer, even with the simple software, could already detect what I wanted to detect. And I also wanted to see whether this is now possible with glass bottles. So I just pressed the color changing material against those glass bottles with the system that I've showed to you, and let it run, or let the RGB images run through my software, and then detected those masks. Once again, I just could compare them to the original mask that we see over here, and then we can see that there is still a highest overlap for the right bottles. However, of course, the detection, the more diverse or the more difficult or more detailed these textures get, of course, the detection will also suffer from that problem. So we can still detect it. However, if we want to increase the amount of bottles that should be detected, one could probably increase or optimize the parameters in the system, or just switch over to maybe artificial intelligence. But now with that being set up, I think I could show that this problem can definitely be solved with such a gripper. And so the engineering task in my work over here is more or less done. And since I hopefully, when finishing that, will also get a Master of Science, I wanted to work on something more scientific. And Matthias pushed me a little bit in the direction of metamaterials, not only because he knows some research groups working on that, but also because it's an extremely fascinating research topic. And so I also wanted to work on that field and wanted to see whether I could improve this research field by implementing a color-changing material. But first of all, let's understand what mechanical metamaterials are. And mechanical nanomaterials are materials that are defined by their structure rather than by their composition. So unless, or not like other materials, they are usually not having properties based on their atoms or molecules they are built up, but therefore by their structure that we give them when designing it. And the cool thing is we can even reach values for those mechanical devices that cannot be reached in nature, like for example negative Poisson's ratios, materials that are called authentics. And what we can see here on the right side. So a material that once we press it in one direction will also be pressed in the other direction instead of increase in thickness like it would be done for most of the materials that we can find in nature. And another thing which is also called metamaterial is a multi-bistable material. So here we can see an example of a bistable material which has two stable states. So most of the materials that we know, once we deform them, will either be destroyed after that or just move back into their original shape. And with those multi-bistable networks, here with this just bistable state thing, I can just press it through and snap it into another stable state, and therefore have basically two different properties of the material, either in one state or in the other state. And once we apply more of those things next to each other, we end up with a network with a lot of stable states. And this is where I wanted to work on a multi-bistable metamaterial that was developed from a former research student, PhD student from Harvard University called Diane Yang, who invented this cool big multi-bistable network that we can see here on the left side, which is nothing else than a die which has a lot of holes in there, alternatingly being thin and thick, so 3 to 5 millimeters in diameter, and having a high aspect ratio. And once we look at that die, of course, we can either press against it from one side or the other side, and therefore let it be a rectangular which stands or which is laying. And since we don't want to press against it all the time, and if we press against it, of course, it's not a metamaterial yet because it will snap back once we move our forces. He had the beautiful idea to just apply it back and a top layer to that and evacuate those cells so that the atmospheric pressures pressing against that object and it's therefore automatically snaps spontaneously either into into the upper state or the lower state, and so we get a material with 2 stable states or more stable states than 2 that we can just compress and snap between a standing rectangle or a laying rectangular. We can see over here on the top, on the right side, that this even was shown in his paper as well. So he can just snap through from the standing to the laying rectangular, and he could even create an arbitrary shape by just stopping this pressure mechanism. And the middle part over here, where he then had a combination of both of those 2 structures. And I wanted to work on that material and see whether I could get more information out of that than as we can get it right now. And so at first, of course, I also needed to learn to produce that material, which at the end was extremely tricky and took me way much more time than I planned to. However, we will come to that on another slide. Maybe let's first look on the production itself. So what we need for producing that material is once again the negative mold of that metamaterial, then filling it up once again with the soft material like Ecoflex, the same that I just used before, letting it cure inside of the mold, and then attaching a top and a backing layer, which is still uncured, and let it cure inside of a vacuum chamber, so that there will be vacuum inside of those cells once curing. And then once it is cured, we can just remove it from the vacuum chamber and will spontaneously snap into one of the stable states. And then we can use it as a metamaterial. And now my goal in the thesis over here was that I wanted to attach this color-changing material as a front and back layer to this multi-bistable network to see whether I could gain more information about this network. First of all, knowing where those cells are, which is more difficult to sense if there's a black or if there's a backing layer and the top layer out of the same material. And I also wanted to see in which state those cells are, so whether they are currently laying or standing, which is difficult if we don't know the edge conditions of this whole die. And I also wanted to know how the topography changed in the relaxed and unrelaxed state, and how active or defect cells inside of such a network influence the overall behavior of that network. And for the first point, just needed to figure out how to apply the color-changing material to that die, and we can see that once I was able to do that, it was quite easy to now detect where those cells are in the network. So once having the network with the same material as top and backing layer pigmented in black or without any pigments, we can see that the detection of those cells is quite difficult because the contrast between the background and the cells is not so high. But with applying the color-changing material, it was easy to detect those cells, and we even get more information because we see different colors on there that could be needed as well. And once I was able to show that I can see those cells, then it's not too difficult anymore to sense the state of those cells. So I just developed the software with this graphical user interface, and then I took an RGB image of the surface of that metamaterials being in one of their stable states. So here standing, so snap through in a standing rectangular. And then I could just load my RGB image in the graphical user face that I developed, and then grayscale that image and binarize that image, and then with a function that detects ellipses inside of such a image, I could detect where the ellipses are and in which direction those ellipses show. So here, for example, we see the ellipses are standing, so we can also say, okay, in this section of the metamaterial, we already know the state of the metamaterial out of just one RGB image. And to analyze how the overall network behaves, I definitely needed to have a bigger network than that one over here, because what we can see is that I just have a few cells being in that network, and as mentioned, the production of that metamaterials, especially the upscaling, was extremely difficult due to the high aspect ratio of the holes inside of that material. And we can see that this network over here consists of probably 49 cells, and one more bigger problem that I figured out when playing around with that material is that if we have a look on the edge cells, which we can see here on the left side compared to the middle cells, what we see on the right side, by even applying just a slight vacuum, there is a round-shaped cell on the edge and a more, let's say, cylindrical-shaped edge in the middle part. So the edges on the cells on the edges are influenced really much by the walls of the metamaterial, because they are a little bit thicker than the walls on the inside, and therefore deformation doesn't take place with those cells anymore. So I had the problem that I ended up with an even smaller network that I could use for analyzing, because the outside cells were influenced too much with the edge of the whole metamaterial. And so all cells, usable cells that I could use, were basically all cells in one row, minus 2 to the power of 2, and this ended then up in only, let's say, 9 usable cells for that object over here, which is not that much. And so I knew upscaling is needed, and this took me around 2 months probably to do that. So I had the small metamaterial, what we see here on the bottom right side, standing in front of the big metamaterial, and this upscaling process, as mentioned, was tricky, but needed to get to know more about the influence of those overall network when applying defects or anything like that. And once I was able to do that, we can see that by applying the color changing material, nothing changed. So I could still do that even in an upscaled way. The production was the same and worked out quite good. But I wanted to just recapitulate the steps to get back to get to such a huge system over there. And as mentioned, the high aspect ratio and the extreme thin sub-millimeter thick walls over here have been a huge problem when trying to remove the metamaterial out of the mold, because they're usually teared when trying to do that. And so I played around with different 3D printing approaches, so I've used deposition modeling or stereolithography and tried around different materials. I also tried different mold releases and several lift-off techniques, and then after time figured out that at least for Echoflex, it is the best to just use the highest printing resolution. So if it is financially possible, then always use stereolithography, because it has way much more flat edges. Then, of course, I filled up the Echoflex with syringes from the bottom to the top in the mold. Without doing this, I figured out that the Echoflex hardens too fast, so that there will be air bubbles encapsulated in the whole system, leading to tears once trying to remove that. And I also used man-ease release as the mold release, and with all the other mold releases, the curing process of the Echoflex was inhibited. So this one was the only one which worked out. And once I had this huge network that we can see over here, we can already see that there are also different colors occurring. However, I could shift around the surface that we see over here. For example, the red points in the middle of the cell or on the edge of the cell, or the green points at the walls of the cell. And when shifting that around, I was able to always see red color for each point on the surface. And that meant there are basically, or there's basically only one way which could happen when the cell will be soaked in by the vacuum inside of those cells. And so the first way that could happen is just that the soaking process of the vacuum is so high that the color changing material will be soaked into the cells and therefore changes the thickness of the layer due to stretching. Or the other option is that it will just be soaked in, and due to the deformation of the metamaterial, it will have a color change only by the viewing angle under which we observe the cell. And so that I knew that when I observed this object from different angles and saw always that there's a red color occurring, I knew that the first option, what we see at the top side, cannot occur, because then we would have a different peak wavelength reflecting. And I also measured in the 3 positions that we see over here, 1, 2, and 3, so out of the cell, inside of the cell, and the edge of the cell, what is the peak wavelength under a perpendicular angle, and I could see that the peak wavelength is the same for all of them, so there's no stretching occurring, and the color change only occurs by a soak-in process of that overall system. And this is a huge information that we gain, because with knowing that, and knowing that we have a Bragg mirror now distributed over the whole system without a different thickness on the refractive index layers, I know that I can just take one RGB image from the top side of that, whole object, of that whole metamaterial, transfer that RGB image into HSV room, and by knowing that we have a Bragg mirror, I also know the shape of the spectrum of that system, so I could convert it into U value and then get out the peak wavelengths of the overall system. And from that peak wavelength, and knowing the formula of a Bragg mirror, I could calculate back the angle under which I saw all the points of the surface of that material. So I basically ended up with getting the surface angle distribution of that overall system. And that is a huge information, because when I, for example, use this color changing material on top of a metamaterial where I applied some defects on top of there, we see how all the cells shape around those defects and will be influenced by those defects. And we get different colors occurring, and we know that they are only occurring due to the angle variation. So we can calculate back the surface angle distribution, and unfortunately I haven't had too much time for that, and I also need to mention that my skills in coding are not that good, but there are some PhD theses out there mentioning that it is possible to use a surface angle distribution and calculate back the whole topography of such a surface. So with just one RGB image that we take from the surface and applying the color changing material, we could basically recalculate the whole shape and the whole three-dimensional surface of that object without any problems. And to see that, the power of that material is quite fascinating. And now let me come to the conclusion and outlook of what I've done in my work. So let's just recapitulate the 3 chapters. First of all, the sensor verification. I think I showed that it is possible to create a color dynamic material that can be used as a distributed soft sensor in the field of soft robotics. And for the tactile soft robot gripper, I think I've shown that there is a basic concept that might solve the solution, the problem which is currently occurring in the German beverage and bottle recycling system, to get those textures and to sort back those bottles with a machine. And then for the metamaterial, of course, when applying the color changing material, we will get more information about the state of the cells and where they are located, so we can unlock previously undetectable knowledge about those states. And as an outlook, I would just hope that further students, or maybe myself, is just optimizing the bottle recognition system so that it could also be used on a tube-shaped system, because right now detection software only works for a flat-shaped system, and it could maybe be enhanced by using an artificial intelligence instead of my simple binary comparison approach. And it might also be helpful to produce the Bragg mirror in infrared, or with an infrared background, to have an overall black sheet when looking on that, but once we press it on top of the texture, only the texture itself will pop out in nice colors. For the metamaterial, it would be nice to develop software to recreate this topography, to also see that it really works, and not only have my words that say that there is a PhD thesis out there which mention how that works. And also it would be nice to build up a closed loop system of that overall system, so having a camera being placed over the color changing layer here on the metamaterial, and then some actuation inside of those cells. And then by giving a computer the information about which shape we want to reach, the system could then arrange the shape automatically. And of course, since I have been lucky to be one of the first researchers to have the chance to work on that material, I hope that in the future there will be even more people who are applying that material to metamaterials and soft robots, since it's soon going to be published and then it's open for all the researchers, and I just hope that it hits the ground running. And since all this work was not possible only by myself, and there have been a lot of people standing behind me, I hope I'm allowed to say thanks to a few more people. And first of all, of course, I need to say thanks to my PIs and supervisors. So from the German side, I need to say thanks to Uli, who supported me extremely during the application process, and already since my third semester, so almost 5 years now, where I listened to his first lecture, Optics and Solid State Physics, and came in contact with optics and photonics. And since then, was fascinated to work in this field as well. So thanks for supporting me that much. Same for my PI here at the US, Matthias. I can now say I think I have never seen such a cool professor before, picking me up from the airport on the first day, but also like all the question sections inside of the office or in the lab, and all the time that you spend, and helped me that much. And even ending up with a barbecue in your house in Hull with the whole research group, or fireworks on 4th of July on a sailing boat out in Boston Harbor. It was a really cool time, and I really enjoyed my time here in the US. And then, of course, my mentor Benjamin, who developed that perfect and really, really cool material that now, as mentioned, is soon going to be published. And I can just recommend everybody of you to also work on that. He introduced me into working in the lab, especially here at MIT, so I'm extremely grateful for all the advices that I got. And I also need to say thanks to the whole LBPE team, Hannah, Max, Anthony, Jan, Andrew, Turga, and Sean, who have been around here and answered all my questions. And all the Thinker sessions, the C-series, and the lunch breakers we joined together have been a lot of fun, and I will definitely think back of that my whole life. And I especially need to say Max, because he spent the most of the time with me down in the lab, and without him, or let's say the other way around, having a mechanical engineer as a friend in the lab is extremely helpful as an electrical engineer. Without him, I would have understood not half as much as I have with CAD coding, 3D printing, laser cutting, and all the rapid prototyping stuff. So that was a huge help. And then at last, of course, my slides are stuck in. My family, my parents, Anna and Klaus, who should hopefully also watch right now. Thanks for supporting me during my whole life, also during my studies, and especially during my time over here at MIT, not only financially, but also ideally and mentally, with all the calls in the weekends, especially at the first time when I came over here. Being alone in a new country is sometimes weird, and it was really helpful to have them around all the time. And same for my brother, whom I am extremely proud of, who also visited me over here at Boston, and we got to Canada together. He brought me most of the bottles that you have just seen here in the in the thesis, so it was kind of the most expensive import of beer bottles I think ever done before. And then of course my beautiful fiance over here on the left side, who supported me the past 10 years, also doing my whole study, was with me the whole time. And I'm extremely happy that she's with me, and I'm looking forward to celebrate her birthday with her in 2 days in Germany. So one nice reason to go back and to see her again. And of course, there are way more people supporting somebody doing a whole master and doing a whole study. Of course, I cannot mention all of them, but at least I can show you their faces for a few seconds. So these are the people that supported me the most in the past years, and I'm extremely grateful that they are around me and supported me and took care of me in the past years. So thanks for that. And with that said, I can only say thanks for listening to my presentation. And now I'm not sure whether I'm ready for questions, but I think I have to be. So question section is open now.